All right, welcome to another episode of Polly's Introduction to Computer Networks. All right, so hey, there's nothing new today except that the gentle reminder the test run session is 10 minutes after the lecture today. But I'm happy that some of you have already passed the test. And we do have a case. A student tried to use maybe the smartphone to do the headshot. But you see that you need to have something to hold your smartphone up so that it can take your headshot steadily. All right. So you see also that it's a good thing that you try to do this test run to make sure that your setup is okay and you don't have to worry about it later. Good. So first topic today. Oh, yeah. By the way, good morning, Gladys and Vincent. So to continue from yesterday, we've already introduced what web cache does. Today, Polly is going to use one example, but through 3 scenarios to show you the value of using web cache. So the first video is the example in scenario 1. Good. The example. Setting is this. Servers up here, client down here. So they're part of the institutional network here. And the servers are connected to the public internet. And the internet connects to the institutional network through an access link. Let's assume that the clients here are browsing the web, requesting objects down from the server. The average object size being 100 kilobits, and the average request rate being 15 objects per second. Then multiply the two, you get the average bit rate, okay, coming down this way. Right? And that is 1.5 megabits per second. Now, let's see. Round-trip delay from the institutional router to any of the origin servers and back. That's set up to 2 seconds. And the access links rate 1.54 megabits per second. And the local area network link rate 1 megabits per second. Now with these, we will be able to calculate the local area network's utilization. 1.5 meg divided by 1 gig, that's 0.15%. But here, 1.5 meg divided by 1.54 meg, that's very close to 99%. And that is a problem if you recall. There's this component called queuing delay in the internet nodal delay. For transmission over a hop, there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. And the queuing delay is very sensitive to the utilization on the link here. Right? So let me take you here. Queuing delay. Just in case you kind of forget about it. It's very case dependent, and the determining factor is the utilization, which we call back then when we were talking about internet delay, the traffic intensity. So this is the amount of input, and this is the output capacity. You see, utilization again. When this is very small, queuing delay also very small. But as it approaches 1, delay becomes large. When it exceeds 1, delay is actually approaching infinity up here. All right? So close to 1, close to 100% delay, just very long. Okay. Let's come back here. Therefore, if we want to calculate the total delay of web request and object download, it will be round-trip delay here, plus round-trip delay here, plus round-trip delay here. 3 components: internet delay, access delay, and LAN delay. Internet delay, we already defined it. Just make it simple. Just say that it's only 2 seconds. But hey, here, fully utilized link with high queuing delay, it's going to be very long. Let's just say that it takes minutes. It could be even higher. And the LAN access delay, now this is very low because utilization is super low. So let's say microseconds. Right? So 3 components, which one dominates? Yep, queuing delay on the access link dominates. So bottleneck where? Here, in terms of delay performance. How do we fix this? Let's look at the second scenario. All right, second scenario coming right up. In scenario 2, let's try to address the issue here, because this is the bottleneck link where the delay came from OC. And let's blow it up 100 times. How about that? So using a fatter access link there. The result is that the access link utilization is also reduced 100 times. less than 1% utilization, you can imagine the queuing delay being very, very short. That brings this component of the delay down to milliseconds. Now, why millisecond? If you recall trace route testings that we did earlier in chapter 1, right? What was that? Quiz 3 or quiz 4, isn't it? Yeah, most of the delay we see between two routers are what? Tens milliseconds and maybe 100 milliseconds at most. So if there's not going to be much queuing delay, yeah, the delay is at this scale. So 2 seconds, milliseconds, microseconds, which of these three components dominates? Obviously, 2. And from scenario 1, we have minutes of delay, to scenario 2, we effectively bring down the total delay. All right, great. Is there any catch? If you think about it, hey, bringing the access link capacity up 100%, that is actually not cheap. So increasing access link speed, no, not cheap. You need to purchase the new cables, of course, but you might also need to do groundwork. Okay, remove the old cables, install new ones. Just think about the labor cost there. And in addition to that, you might need to upgrade the routers there connecting the high-speed link, just so that you can accommodate potential traffic volume. So, yeah, very costly. Now in scenario 3, let's see if we could introduce something else instead of blowing up the capacity in the bottleneck link. All right, so you see, in scenario 1, because of the queuing delay in that bottleneck link, the delay gets really long, minutes. So in scenario 2, we try to expand the capacity of the bottleneck link, and you see that the delay is lowered. But there's a cost of doing that expansion of the bottleneck link. It's very expensive. And therefore, scenario 3, you see, web cache is a solution that brings down the delay and yet not very expensive. In scenario 3, instead of blowing up the access link, let's install web cache here. I'm calling it the local web cache because we are very close to the clients. All right. Oh, and yeah, I meant local web cache here. Okay. So that you are not confused with the local cache we've talked about in conditional get, where that cache is actually very, very local on the hard disk of the user. All right. So we are only slightly local here. So let's see. Good. So everything else stay the same. All we did is just install the machine. Now, if I ask you, changing this to 154 megabits per second versus adding a server machine, which one is more expensive? Yeah, you probably guessed, right? Labor costs, routers are expensive, cables sometimes can be expensive depending on the distance between the physical distance between the two routers. For your information, this could take millions of new Taiwan dollars. But installing a high-end server machines, it only takes this much new Taiwan dollars. So that's about 2 order of magnitude difference. Yeah. Installing web cache, so much cheaper. Great. Now, let's see if the delay is also going to be better. Or maybe if this is cheaper, then delay is going to be worse. Now, let's try to calculate this. We know the LAN utilization, and so maybe the LAN delay is also about, yeah, microseconds. But access delay, well, we'll have to know the access link utilization in order to estimate the access delay. Therefore, question mark, therefore we couldn't quite yet estimate total delay, right? But then, so this has something to do with the traffic that needs to be brought down this way, right? How many objects will be coming down this way? That seems to be the question. And if you think about it a little bit more, isn't that depend on, for all these web requests we send to the proxy server, how many of them are going to be satisfied locally? Therefore, we could just, transmit the object from the web cache through the LAN to the clients without going all the way up to the servers. So that is this thing called the hit rate. Okay, amount of the proportion of the requests being satisfied locally, that's the hit rate or the success rate. Yeah, let's suppose the hit rate is 0.4. Then we see 40% of the requests will just stay here. Only 60% goes out and back. Great. So we know then the access link here, the utilization is 60% of the, access link. 60% of the scenario 1. And how much is that? 60% of the traffic, then it's only this much traffic on the 1.45 megabits access link, only 58%. So we cut the utilization from 99% to 58% if we ended up having this hit rate. Now let's calculate the total delay. So 60% of the time it's going to be long delay all the way to the server and back. 40% of the time just on the local LAN. Now, local LAN delay, we've seen earlier, microseconds, but I'm using the milliseconds here just to take into account the traffic here. So if we go out, request object down to the web cache, and then web cache serve the local client. We have one copy down here and another copy down this way. So the LAN here, the traffic potentially could also be higher. So let's use milliseconds just to be safe and take that extra traffic into account. Now, for the 60%, we'll have to go out and back, right? So this is very negligible. This part is what? The key component. This part, 2 seconds, we know for sure. So what's remaining is just the delay here on the access link with 58% utilization. Well, how much delay is this? If there's a lot of queuing delay, we go minutes. If very, very low, only 1%, we go milliseconds. So minutes, milliseconds, well, that's, say tens milliseconds or hundreds milliseconds, right? So I'm trying to be a bit generous here and use 10 milliseconds only. And so total delay here about 2.01. And 60% of that plus 40% of milliseconds. The dominating component is the 2 seconds. So you see here, the overall total delay on average is going to be about 1.2 something seconds. Is this better than scenario 2? It is, right? Scenario 2, you have at least 2 seconds. So what's amazing about web caching is this. The benefit is not just that it's cheaper, but the delay is also lower. And the traffic coming down this way is also lower. Hey, we did not spend any money here, and we also saved some bandwidth here as compared to scenario 1. So there's more traffic can come down this way. Isn't it nice? And that explains why we need web caching, right? It's to reduce the delay. This is also called the response time, okay? That meant the time it takes to issue the request all the way to the server and bringing down the web object. The round-trip delay of the request and response messages. It also reduces traffic, save a lot of bandwidth on the access link, and it's very cheap. Now, an extra benefit we didn't talk about is because we did not assume the uplink bandwidth of the servers being the bottleneck. If the server is poor, meaning having a poor content providers out there, then, let's say that the server here is poor. It cannot afford too high bandwidth uplink. Then reducing the amount of traffic going this way also saves poor content providers some resource, some money. And so web caching there also help the poor content providers to deliver content, all right? And this could be a good thing because most of the NGOs, they might also have information to disseminate, but they couldn't provide good uplink bandwidth. And that actually gives rise also P2P file sharing. The idea of P2P file sharing is also, hey, if I have the copy of the content and another peer grab a copy of it, then this other peer can help serving the other peers. So that peer there is working pretty much like a web cache, isn't it? Like a proxy server. So you could actually think of a P2P network, a network of these proxy servers. Okay. And you saw a bit already. Next slide. Coming next is going to be the second application in chapter 2. And we'll look at how FTP defines its application layer protocol.
All right. So, hey, we're done with the web browsing, the application, and the supporting protocol, HTTP. Again, when we're designing a protocol for an application, we think about what? The communication model. Client-server or peer-peer? So is HTTP client-server peer-peer? Client-server. We also think about, oh, hey, to connect the client and server, we need to establish a socket, isn't it? But to specify a socket, we need to set the port. For web, it's either port 80 for HTTP, or I think 443 or 433 for HTTPS, the secure HTTP. And then we need to decide what is the underlying transport layer protocol, isn't it? And in the case of HTTP, it's the TCP. Also, last week, we actually went through these HTTP request messages and response messages, isn't it? So there are messages defined, and they all have their own syntax and semantics. And there's also a certain ordering between the sending of these messages. So keep in mind, communication model, the socket they're using, TCP or UDP, and then the message types and formats. When we are looking at the other applications, the rest of the chapter. So coming up next is FTP. It's another protocol that is actually superseded by HTTP. So let's take a look at the mechanism. FTP, the File Transfer Protocol. This is the second application layer protocol we're learning here. So see if you can identify what is the communication model, what is the structure between all these entities involved, and what is the underlying transport layer service, and what are the message types, syntax, semantics, and how are these messages exchanged. Pay attention to these. So first of all, what is the communication model? You see here, client server. Client is always the side initiating transfer, so over here, this side. And server is always the one that's far away, it's over here. All right. So what you see here is FTP is to provide transferring of files to and from the remote host. Server here is essentially allowing the users or the client access to the hard disk here. Okay, so it's a little bit like Dropbox. Okay. So a distributed file system in a way. Good. Now, file can go this way as well as this way. So you see here, it's bi-directional. Good. The protocol is defining this RFC. Number is only 3 digits. You see that this is one of the earliest internet protocols. The server there is sitting on port 21, another well-known default port number. So whenever the client needs to initiate communication, it goes to port 21, where the FTP server will be sitting on. And by the way, 21 is also the port number that Poly confuses SSH's port number on. All right, so let's take a closer look at the message exchange. All right, so FTP clients contact FTP server at port 21, this we know, and specifying TCP as the transport protocol. So FTP there uses TCP just like HTTP as the underlying transport layer service. And then the client will try to authorize itself into the server over a control connection. So what I'm depicting here is also what's going on here. The client will establish a control connection towards port 21, okay, at the remote host. So messages saying, I want to log in, here's my password, will go on this connection. After the client logs in, it's going to browse through the directories, okay, in the remote hard disk over here. So the commands changing the directories around is going to also be sent over the control connection. When the server receives a command for a file transfer, okay, so command for file transfer also travel this way as it's also a command, so it goes on the control connection. But the server now, okay, will open a TCP data connection going back this way. Okay, so that is depicted here, the data connection running on port 20. After transferring a file, the server is going to close the data connection while this one remains on. If the server needs to send another file, it would start yet another TCP connection and send the file over there. Okay. So such separation of control and data-based content on different channels, okay, in communication, we call it the out-of-band communication. If you think a little bit more, in HTTP, there are two messages, right? HTTP request, HTTP response. Yeah, which one is data? Which one is control? No, in fact, each of these messages are both control and data. In HTTP request, we do have comment, right? Get, post, head. But in HTTP response, we also have the status line. So these are obviously control. But in both messages, we also have the body entity. If you use a post comment in HTTP request, you might be sending also some data up to the server. And very classic web response, the entity body contains the web object. So in HTTP, communication is in-band. One word, in-band, right? Data and control messages are bundled together and going on just one connection. FTP, very weird, out-of-band communication. Another thing that FTP differs from HTTP is this. HTTP being stateless, but FTP is stateful. So FTP server here actually store information about the client's previous visit, including where this client at in the directory structure before the client logged out. Okay, so next time when the client wants to log in, the server will take him directly to whichever directory the client left. So the client can continue working on, downloading files or uploading file in that space. Similarly, if you log in as a client, you might get a message from the server saying, oh, you logged in previously at a certain date and certain time. Okay. So this is sometimes a nice thing to do because you might want to know if there are unauthorized logging and authenticated logging, meaning someone stole your password and then use it to log into the FTP server.
All right, so you see that in FTP, the communication model is very similar, right? Client, server. And it's also using TCP as the underlying transport layer protocol. But what differ are these. First of all, in FTP, you use two ports to connect the client and servers. One port for the commands, the control messages. The other port for the data. So if you think about HTTP, we use just one port to send both control messages and data. So what are the control messages in HTTP? Yeah, those are the command line or the request line, as well as the header lines. So those are not real data. They are actually just for the purpose of communicating the server and client. So they know properly how to send the data. So the port for data then we'll be just sending the data part of the HTTP response. Okay, so something similar, but something different. There's another difference in a FTP if you notice. HTTP is stateless, but FTP stateful. Okay, great. So, hey, we have not yet talked about FTP's messages. Let's check out what are the message types and how they are defined and exchanged.
Next are just a few examples of the messages being exchanged between the FTP client and server. So these simple comments are messages the client sent to the server. And server typically return these return codes, right? So very much like the HTTP request, the control part sends comments and necessary information to help the comment to be executed at the server side. And then the server returns certain code, phrases, and explaining of the code and the phrases. All right, let's look at the example. Oh, and by the way, again, in FTP, messages are in ASCII text, right? Data, however, on the data connection could be in bytecode, all right? So control connection there is always sending ASCII text messages. And control connection there is also allowing the server to send back status code. Okay? So these and these all on the control connection, only the data on the data connection. So let's begin. User, capital user, space, username. Hey, you guess, this must be a user trying to log in and providing the username. So this is a variable, so comment, argument. And this is going to be sent through the control connection to the server. Server check. If the user does have an account on the server, then this is what the server sends back. 331, username, okay. And server asks, could you send me the password? So, hey, a hacker might have figured out the username, but not necessarily the password. So client here sends pass, again, capital, space, password, over to the server. And then the server can perform the rest of the authentication. So you see, capital PASS, capital USER, these are special words, okay, in the comment messages. All right, so each followed by an argument. List, this is a special comment, no argument required. What it does is to return the list of files, okay, in the remote directory. So upon receiving list at the server, server sends, okay, here are the files in the directory. Retrieve, RETR capital, space, file name. This is now officially to ask for a file from the server. Retrieves files. The other way around, if we want to store a file, upload the file to the server. Then store, capital, file name. Now, here are some status code and phrases the server might respond. So, 125, data connection already open, transfer starting. So this might be the server responding to a retrieve command, okay, setting up a data connection, and then next bytes are gonna come. Or server might find that, hey, there's not enough socket to open, or there's not enough bandwidth, can open, data connection message might be going back. 452, error writing files. Oh, okay, so this is this case. If the client wants to put the file onto the server, and if there's not enough disk space, or if the client doesn't have the access right, the readable access right, the writable access right, then the client gets this message, 452. Okay, so that's FTP. We see again, an application layer protocol defines communication model. Is it client server, P2P, or hybrid? An application layer protocol defines also what is the network structure. In both HTTP and FTP, it started off very simple, one client, one server. But you see earlier in HTTP, it kind of grows a little bit, having these proxy servers in the middle, helping with the transfer. In every one of these application layer protocols, we also need to define what are the messages to be exchanged and the order they exchange. So we see here examples of messages defined for FTP and how they're exchanged, okay, in the previous slide. Okay, through the control channel, yeah, logging messages, checking directory messages. So this is FTP.
Yeah, so you see, FTP, there's one more difference, isn't it? In HTTP, you could actually have a web cache there helping the origin server. Okay, but FTP doesn't have that either. So in a way that when you're thinking about designing an applications supporting protocol, it can be client server, but the structure of connecting the client and the server can be actually more advanced, like having an intermediate server, for example. In fact, the next application, email, you will see that it is also working in a client-server model, but it's actually working in two levels of client and server. You see, again, the communication model, even though the entity is still clients versus server, but the structure of these clients and servers gets more and more complicated. So here's email's communication model.
2.3. Emails. So this application is a little bit unusual. It's supported by not only one application layer protocol, but multiple ones. And we'll talk about it more. Email application. It's got three major components. First is the user agent. This is the software running on the machine closer to the users. And mail servers are the software running on more resourceful machines farther away from the users. And among these mail servers, it runs this protocol, SMTP, the Simple Mail Transfer Protocol. These we'll also talk a bit more about. Let's start from the user agent. They're essentially the email readers. They allow us to write email, edit email, read emails. Outlook from Microsoft is one mail reader that's very well known. Thunderbird, I don't know if you know about this one. This is from Mozilla. So the company that produces also Firefox, the very well-known web browser. iPhone comes with a built-in mail reader. Google is also trying to push for a Gmail mail reader. So there are so many of these email readers these days. Now, keep in mind though, the actual emails are all stored on the servers, not on the user agent these days, all right? Now the mail servers. It's got these three major components. The mailbox, which contains all the incoming messages per user. So these are the yellow boxes. When emails come in, they will be sorted out and then put into the email boxes depending on who the receivers are. Second component, the message queue. Those are the green queue over here. So messages that are going out will all be stored here temporarily and waiting for the receiving mail server to open up and then accepting the emails. So SMTP protocol there is to allow the sending server and the receiving server to communicate. Now here in particular, the sending server there is called the client of the SMTP protocol, and the receiving server is, on the other hand, the server of the SMTP protocol. So you see a little bit here, the SMTP protocol is to provide mail receiving service in a sense. So client here requesting service, server here allowing emails to come in. If you think about it more, it's got two levels of communications in the email application. So this is one between the end users and the local mail server. Okay, fetching email or pushing email out. But there's another level, which is among the mail servers. All right, so sending mail server is the client of the higher level communication. Receiving mail server is the server of the higher level communication. Then the SMTP protocol. So this is the actual application layer protocol defined to support communication in emails. So let's see, what are the underlying protocols and what is the communication model and what are the messages defined? TCP you see here. Therefore, SMTP is to support reliable email receiving service. It runs on port 25 and the transfer is direct between the sending and the receiving server. The exchange, very simplistic, 3 phases, handshaking, and then extra transferring of the emails, and then closing. Opening, closing, the extra transferring of the emails in between. The messages are also simplistic. They're just comments coming from the sending server, responses coming from the receiving servers. So comments in ASCII code, just like HTTP, just like FTP. Responses, status words, status phrases, status code, just like HTTP and FTP. They all run in the ASCII code. Now put all 3 major components together and let me illustrate with a concrete scenario. Alice here is sending an email to Bob over there. All right, so Alice will need to start the user agent first to compose an email. So in the email, it will need to specify the receiver. And then the user agent will send the email to the message queue, okay, in the local mail server. So that is step 2, emails going to the message queue. And then the client side of the SMTP, which is here, this guy is the one sending, and this Bob's mail server will be the one receiving. So this is the client of SMTP. This is the server of the SMTP. So client side of SMTP will open up a TC connection. Once the server is allowing the connection, then the client can begin sending Alice's email. So that email will travel, and the server here of Bob's will check whether the receiver is Bob, and therefore putting the email into Bob's mailbox. Right? So email goes to Bob's mailbox. Lastly, when Bob now joins the internet, invoke his user agent, then the agent already pre-configured to connect to the incoming mail server will then fetch the mail messages, and that's when Bob gets to read the email.
Yeah, and guys, it's time for quiz. This is quiz 12, and then we go to the whiteboard mode so that I can scribble on the side. So you see, in the Alice and Bob scenario, Alice is the sender, so you see SMTP works in a lower level. So this is a client, this is a server. So this is one that's sending email, this is the one receiving email. But you see also SMP working in another level, a higher level. Okay, this is the one sending email, this is the one receiving email. So from Alice to Bob's mail server, the whole thing is done by SMTP in 2 levels. But for a reader, okay, for a receiver to read emails, it's actually what? The reader needs to invoke the user agent and then fetch emails
from Bob's mail server, from receiver's mail server. Okay, so let me just tell you ahead of time, that protocol is not SMTP. It's recently more popular are the POP3 and IMAP. Okay, so the protocols are different, and they are called the mail access protocol. All right. So the question is, however, hey, why not use SMTP all the way to Bob's user agent? Okay, so why can't Bob's mail server just use SMTP to deliver the mails straight? All right, now let's go to Discord, week 5, quiz 12 channel. Okay, so you see that the quiz side is also there. So gather your teammate, and you guys have only 5 minutes to work on this. Okay, let's go. And you know what? Yeah, I see already 3 teams popping up and providing what they think the answer is. So let's see. Bob's agent, not always online. Okay, that makes sense, right? Are you always online? Well, some of you might be, but most of us, right, we go on and off and on and off. Okay, so when you're attending to the lecture, so you are online, but you are not online reading your emails. But you see, SMTP works in a way what? From the client, you push the emails to the receivers. And so when you're pushing, the receiver needs to be online, right? Otherwise, who's there to receive the emails? But you know what? Let me go back to the whiteboard here. Now you might see how it's making sense in the end. Here, SMTP, the receiver of the emails needs to be always online. And you know what? This is Alice's email server, and the servers are what? Always online. So SMTP will work fine here. Similarly, there's another SMTP another level of this SMTP. So this is sender, and this guy here is the receiver. Is this receiver always online? It is, because it's the receiver's mail server. Servers are always online. But over here, let me remove the markups. Bob. Can Bob be always online? Can SMTP run here to such that, hey, this receiver is always online? No. It's actually the other way around. The sender, okay, of emails, in this case, the receiving end of the email application is always online, but not the receiving side. All right, that's why we use a different protocol, which is more initiated from the client, and then ask the server storing all the emails to send emails when finally Bob is online. Okay, good. Yeah, so you guys did very well. So let me go back to the scoreboard. Yeah. Okay. Maybe Bob's user agent is not always connected to the internet. Yeah, this is definitely the most obvious answer. They can only transfer emails and not receive. Yeah, as Bob's user agent, right? User agent typically send emails. Okay. To receive, usually the user agent also initiate something. Send a command to the mail server to really retrieve the emails. Okay. So I think what Vincent here meant by they are like, Bob's user agent. Okay. All right, Johnny here. SMTP is a push protocol. That's a very good point. Yeah, it's pushing emails out. And Bob there is not always, Bob is not always there, right? So it's not going to work for a push protocol. Good. Endpoint, user agent. Yeah, definitely. Second point, sending user might be offline. Interesting. Interesting. But sending agent can send emails fine. Yeah, so Mark, could you elaborate what you mean by the second point? Endpoint. Bob is not always on connection to fetch. Okay, interesting. Do you mean that the receiving user, right? Mark, I think you probably meant receiving user here. There you go. Okay. Bob has to resend email from the server. Re-email. Because it's taking emails in. Yeah. Yeah, I think you guys get the point. All right. Oh, interesting. Interesting. So, Min Luan is saying that so Bob's user agent only needs to read from the mail server. This way, the server doesn't need to update the mailbox every time a new mail comes in. That's actually something else. It's more like Bob's mail server there can actually stack up the incoming emails and then push all the emails pending in one push. Okay, so this is actually a technique people often do to improve the transmission efficiency. Because that way you don't need to establish a TCP connection for one email and close it. And you can establish one TCP connection and send a batch of emails. Okay, so this is somewhat different. Okay, interesting. That can be one of the reasons.
server to server. Well, Charlie, be careful. It's a protocol from client to server still, but I think you meant mail server at another level. The sending server and receiving server are both servers. But you are right. Bob's user agent is not exactly like a server who are always on. Good. All right, so you see the reason that SMTP only works to the receiving mail server in the entire end-to-end connection. And then we need a access protocol, a mail fetching protocol from the receiver's user agent. Okay, good. And that is exactly the point I want to bring up. But hey, we are not yet done with the emails communication model. So this video coming up is to also tell a little bit about the messages, okay? And a short demo of Poly tries to emulate a user agent or a mail client and see if we can fetch emails from somewhere, from a mail server. And I try to do it through a Gmail server, but nowadays Gmail servers are all secure. Okay, using the TLS. So you will see that Poly run into trouble connecting to these Gmail servers. This is a very simple SMTP exchange. Let me explain the notation. S being the server, C here being the client. Now in SMTP, this is the receiving mail server, and this is the sending mail server. Once the TCP connection is established, the receiving side identifies itself first. 220 hamburger IDU, status code, status phrase. Client here then would in turn tries to identify itself as well. Crepus.friends, that's the identity. And hello here is the command to allow the server to know who the client is. And then server, status code 250, everything is fine. Hello, Crepus.friends. And then beginning from here, we start to see control message exchange. Client here needs to specify who the sender is and who the recipient is. So mail sender is Alice and mail recipient is Bob. So all capital here, mail from. All capital here, receive to. Okay, our special commands as well, just like the hello. So whatever comes after the columns are the mailer and the recipient. So server again are just saying, okay, good, I got it, 250. And from here on, this is the actual data exchange. Data, once again, the command. Email starts from here. Do you like ketchup? How about pickles? And it ends with a single line that has only a period. Okay, so the actual email message is only this short, 2 lines. Last is here, just to close. Okay, server will say, message accepted, everything is fine. Client then issue yet another command to quit the session. Server says, all right, goodbye. Very simple. To set up connection, to do the email exchange, and to close the connection. In the email exchange, there's the control message part and then the actual data part. And that is an SMTP message exchange among the client and servers. Let's try now to telnet to an actual mail server at port 25 and see what the server would send back to us. And then we could try to type in some of these comments out and see how the server responds. So let's go to the demo mode. Now let's try telnet to a mail server at port 25. Telnet, which mail server? Actually Googled up Gmail's mail server. The name is this, SMTP, how appropriate. gmail.com, 425. There we go. IP address being 64 something something. And this is a message coming from the server, 220. All right, so SMTP, gmail.com there is identifying itself. And then ESMTP, okay, it's saying more. I'm not quite sure what this is. Right, so E must be something and then SMTP. So this might be a special variation of SMTP, maybe the encrypted version, I'm guessing. So let's try typing up some of the comments. For example, hello, and coming from us.edu.tw. How about that? Great, seems to be working. 250,
So the server say, ooh, address service. That's really polite. All right. Then let's try the next comment we saw earlier, mail to. And let's have Gmail sending to pollys email address. How about that? What is this? 530, 5.7.0 must issue a start TLS comment first. So yeah, it does look like it's trying to establish an encrypted connection. So TLS, if you recall, is what? Transport layer security support. So I'm guessing this is probably the credential, the public key. So I'm supposed to send back the share secret key with the public key as the key to encrypt. But I don't know how to do that. So yeah, let me try it again then. Playing dumb here. polyhuang@ntu.edu.tw. Let's see. No, it's not accepting it. So I have to, yeah, so maybe recipient from, yeah, Polly's Gmail address. How about that? No, it keeps bugging me saying, okay, let's do start TLS. So that's issue this comment, start TLS, and see, start TLS. Oh, cool, it's accepting. That's nice. Ready to start TLS. All right, so then I suppose I need to send back the, I'm already out. So it seems that the establishment process there also has a time limitation. Otherwise, yes, and hacker might be able to hijack something that you have done in the middle. Interesting. So, hey, I got kicked out. So Gmail is a secure email service. Email messages are encrypted. Nice. Good to know. And so that was a demo of trying to telnet to a mail server, actual mail server. You could also try this yourself, maybe from the workstation. Okay.
All right, so that was the messages. As you see in email and FTP, the messages are less complex, much less than the HTTP messages. It's always just a short line where you have comment and the parameters for the comment. Okay, but what's common in all these three protocols? ASCII, readable. All right, great. So it's a good time to take a break. It's now 11:12, so we'll resume the lecture at 11:22. Okay, break. All right, so let's come back to the lecture. There's just one short video to add to email because there's also content of email. And that content of email is also well defined. There's also a protocol for it. Okay, so here's a short video to explain that. And just a few words about SMTP at the end. Once it sets up a TCP connection, the client there can use the connection to send multiple emails. So it runs just like the persistent connection we see in HTTP. SMTP requires text in ASCII code, very strict. And SMTP uses just a single dot in the last line, okay, to determine whether it's the end of the message. Now, if we compare SMTP to HTTP a bit more, they differ in multiple ways, but they are also similar in another way. So this is the first thing they're different. Yeah, the service sort of direction. HTTP is actually to pull objects down, but SMTP is to push objects out. Now, object here I meant email. They are similar in this way. Comments, responses, all these messages are in ASCII text format. But HTTP and SMTP are also slightly different in this way. Each object is encapsulated in a response message. So HTTP server there sends one object at a time, one object per message. But SMTP can send multiple objects in one message. That message is just having multiple parts. So for emails that comes with an attachment, like a big PDF file after, here is the attachment, if there's anything wrong, contact me. So email, the original text at the beginning, and then additional attachments. They can be sent as a multi-part message. So multiple objects in one message versus HTTP. One object, one message. Mail message format. So there's yet another protocol that defines how the email messages should look like. So this will be the data part of the SMTP protocol message exchange. If you recall in the example earlier, there's the opening phase, some control messages being sent, and then comes the actual data before closing. So the mail messages here we're talking about is the content being sent in the data phase. All right, so these messages are not control messages for SMTP. So they are not SMTP. The mail message format is actually defined in another RFC. It's another protocol. So in that protocol, it defines the mail message format. There are two parts only. The header containing a number of header lines, specifying who the receiver is, who the sender is, and what is the subject of the communication. In the body, very simple, just the content of the communication. So note again that I try to clarify. In SMTP, you see mail from. So this sounds like, following this command, you also tell who the sender is. Receive to, after the comment, after the column, you give the recipient's email address. So it sounds a little bit like the to line in the header line and the from line in the header line, but they are actually completely different things. These go in the data part, while these go earlier, setting up a connection ready for data exchange. All right, so that's SMTP essentially. And we had another question. Okay, so this one from Doris is probably very concerning for many of you. Can I blur the background in Google Meet during the exam? Yes, you may. All right, so I think that answers the question. There's just one last video about email. SMTP from the sending client to the sending server. SMTP also from the sending mail server to the receiving mail server. But the last leg of communication in this end-to-end communication is through an access protocol. So this video is to talk about the options of these access protocols. By the way, NTU's mail server for access is POP3, one of the access protocols. So pay attention here. And then we'll switch gear just a little bit and talk about the last part of email application. So we've talked about the flow of sending an email all the way from Alice to Bob, right? So mail access protocol runs here. Okay, so it's this part of the entire flow. SMTP that we talked about earlier only covers email exchange to the receiver's mail server.
in between the receiver's mail server and the actual receiver, it's this protocol that's controlling. So what it does is to allow the receiver to retrieve email from its local server. There are three very popular mail access protocol: POP3, Post Office Protocol, IMAP, Internet Mail Access Protocol, and HTTP. These two, you can see that they are more specifically defined for the purpose, allowing a receiver to retrieve email. The functionality is also similar. First, the receiver needs to authenticate itself, authorize itself, and then begin downloading emails. IMAP, being a slightly newer version, okay, it includes a number of other features, including, for example, we could store the email messages in a more structural way, for example, creating folders and putting certain emails in certain folders. Right. HTTP, however, is special. It's quite fashionable these days. Some of the mail service providers are asking us to use a web browser as the user agent. And then the email server there is essentially also a web server, so that it runs HTTP in the middle and treating each email as a web object. So fetching an email, fetching a web object. Okay, it's the same thing, except that the content is more specifically being emails. And take a closer look at how POP3 works. Okay, the exchanges between the client and the server. The notation is very similar to the exchange we saw earlier in SMTP. S being the server, client is C. So there's an authorization phase and then the actual transaction phase. So authorization phase you see here, the client comments very typically being declaring the username and declaring the password. So you see here, in the authorization phase, server says, okay, I'm ready. Client says, I'm user Bob. So the username there is Bob. Password, being hungry. All right. And server responses with either okay or negative error. It's even more simpler. All right. So okay here, okay here, okay here. Maybe with the phrase after that. And in transaction phase, this is where the emails are actually retrieved. So clients sometimes say this, list. So this is to ask the servers to tell back the list of emails there are. So this is more the index of the emails, and a lot of times just containing the file size and maybe the subject line. Right? It's only until the client begin issuing comment like this, RETR. So this is for retrieving messages. So RETR1 indicates that it's retrieving this email. So this is the index of the email, the size of the email, and there could be other information. Then the server sends back the actual content of the first email, and again, ends with a period, and only one period in the whole sentence. Right? The client can actually delete an email that has already been read, or in case it's a spam. Right? So DELE, very intuitive, being the delete. Quit, also intuitive, being quitting the session. All right? So retrieve an email, server sends an email, client delete an email, retrieve another email, server sends another email, and client deletes yet another email. Q and then plus OK, server says goodbye. So that's an example of POP3 exchange.
All right, so that's email. You see that email is a special application that requires two protocols to make sure that the end-to-end connection completes. SMTP and POP3 or IMAP. Or nowadays, if you're reading Gmails through your web browser, HTTP. All right, next topic is the most interesting among all the client-server-based applications we'll talk about in Chapter 2. It's called DNS. So we'll start by describing why we need DNS. Okay, so here's why.
Next is Chapter 2.4, DNS, which stands for Domain Name System. And before we talk about the purpose of it, let's talk about identifying a person. If I tell you my social security number, my name, and my passport number, which one would you think would be easier to memorize? Well, social security number, 10 digits long. Well, the national ID of Taiwan is also about 10 digits long. You can correct me if I'm wrong. Name, Polly Huang. Passport number, don't even bring this up. Polly does not recall her passport number, as a matter of fact. So very obvious, isn't it? The name is so much easier. Well, that's just how human brain works. Name, form of ID, much easier. Number form of IDs, harder, especially when it's a long sequence of numbers. Well, internet, to identify a machine on the internet, shows a similar obstacle. So hosts and routers, many of them have the IP addresses, right? But these IP addresses are even harder to memorize, maybe harder than the passports. And as you're working on the PAs, right, memorizing the IP address of the workstation, super hard. Even though you've already worked on it for a while, if I ask you to type it up, it's probably still challenging. So what we do here on the internet is to give some of the important machines also a name. For example, www.yahoo.com here is the web server of yahoo.com. So you could just type www.yahoo.com and it quickly leads you to Yahoo's website. Similarly, www.google.com, quickly we reach Google. So hey, how does the web browser know what is the IP address of the web browser given just www.yahoo.com? Well, that is the functionality of DNS, to identify the mapping between the IP address and the name. And let's talk about DNS more formally. So essentially, it's a database of these mappings. So lots of these IP address mapping entries. Nowadays, it's distributed, meaning there are multiple of these name servers. And there's a hierarchy actually connecting these name servers. Some of them sitting at the higher hierarchy and some of them sitting lower. What's a bit special about DNS here is if you hear me saying that, hey, a web service will need to query DNS system in order to find the mapping. So hey, web service is already an application level service. HTTP is already the application layer protocol. So it seems that the application layer protocol, HTTP, there needs to work with DNS, which is also an application layer protocol, in order for it to operate correctly. So DNS, in fact, work with multiple of these application layer protocols, not just HTTP, all right? So name servers there would help all these application layer protocols in order to resolve names to the IP addresses. It's a very essential function. Some might argue that it's one of the core internet functions, which might sit underneath the application layer protocols instead. But now we put it in the application layer such that it's only running on the end hosts. If we need to update, improve the DNS servers, we don't need to actually go ahead into the core of the internet, all these routers to change everything. So that makes changes a bit easier. Right? So there's a very special phrase that the internet designer would like to say, which is complexity at the network's edge. What it means that if you come up with something, some function that's very essential and it could go complex, then let's put it at the edges. Let's have it running on the hosts instead of running in the routers at the core of the internet. Okay. And a good side of doing this is so that we could evolve quickly and the performance bottlenecks can be removed quickly. Right.
All right, so that was why we need DNS. It's essentially maintaining the mapping of host name to IP addresses. You see that the IP addresses are very often hard to remember, but host name a lot easier, right? For example, NTU's web server is www.ntu.edu.tw. So we don't have to memorize the IP address of the web server. Okay. In fact, the entire World Wide Web, or generally the internet, the server are given in terms of their names instead of IP address, except for the PA workstation. All right. And so, hey, from these names to find the IP address, these mappings are very critical, right? When you need to establish connection to a server. So in fact, DNS is used probably more often than any of the applications we've talked about before: HTTP, FTP, email. Okay, to connect to the mail server, you need to have the mail server's host name. Recall in the demo, right? Polly tries to connect to the Gmail server, smtp.gmail.com. After I connect, I see that the IP address of the mail server. But when I'm establishing connection to that smtp.gmail.com, hey, in order for a TCP connection to establish, I need the destination's IP address. So DNS was working there. So in fact, in every one of these applications we're using, whenever there is a need to translate from the host name
server's host name to the IP address, DNS is called. And therefore, DNS is actually somewhat fundamental of all these application layer protocols. And yet, DNS is implemented as an application layer protocol. Okay. And the data of DNS connection, a DNS socket is sent through UDP instead of TCP, unlike the email, FTP, and HTTP protocols. So DNS as an application layer protocol is a very unique existence. Right? So you do want to pay attention to DNS. Okay, some of the harder problems that will appear in the exam are about DNS. All right, so we know why. Okay, and we know that DNS service essentially is that there need to be a server that store all these name to IP address mapping. Okay, so it's a database essentially. Okay, but you see that there are so many mappings. Would it be okay to use just one server to store all the mappings? In fact, for many of the web services or internet services, generally speaking, there will be always a lot more data to store than you imagine. So one server to store all these data usually not feasible. Okay, so before we go on to talk about the communication model of DNS, let me add a little bit more about DNS. The functionality. So as I mentioned, it's to store a lot of these host name to IP address mapping. But you know what? That's not the only function. Okay, it's the most fundamental function. But there are also there are also other functions. For example, how do one know? How does your user agent know the mail server's host name? Okay, of your mail service? How did Polly figure out smtp.gmail.com? In fact, that's also supported by DNS. When you send an email to, for example, huang.polly@gmail.com to somebody at gmail.com, your email user agent asks DNS for the host name of the Gmail server first, and then ask DNS service again to find the IP address of your Gmail's mail server from the Gmail server's host name. Okay, so there are actually two queries back to back in order to find out the IP address of that Gmail server. So DNS, it's actually a quite complex system. Next video, let's find out exactly what functions are provided by DNS. DNS services. There are multiple services actually DNS provides. First is what we've talked about, the most basic one, from the host name to IP address translation. It does three other forms of translation. First is the host aliasing. So what happened often on the internet is that some hosts came with host names, but the host names could be slightly longer, indicating where it is or which one of it, number 1, number 2, number 3. Okay, so those can still be slightly harder for users to memorize. So alias name here is often cute and short and very easy to memorize. So this is where the users know the services are, such as .google.com. All right, so from alias name, DNS allow the web browser to look up what is the canonical name of the server, and from the canonical name of the server, identify the IP address through one of these mappings from host name to IP addresses. So that's how host aliasing works. Second, mail server aliasing, right? So I mean, you must have one of these, right? Gmail accounts. If your friend is sending email to your Gmail account, your friend's mail server will need to know who's your mail server. So who's Gmail's mail server? This thing actually looks very general. It's in fact a domain name, not quite a host name. So what happened in DNS is there are also these entries saying for this domain, gmail.com. Okay, all the emails destined to this domain should send to this machine, smtp gmail.com. This we talked about when we were telnetting to an email server to demonstrate the message exchange there. smtp.gmail.com is the actual mail server for gmail.com. So there are also this entry here in DNS service. Okay, and this is called the mail server aliasing service. Last, okay, this one is a bit tricky, but it's growingly popular. It's called the low distribution service. What it does is this: for a host name, there could be multiple IPs that map to it. So IP1, and then the same host name, IP2, IP3, IP4, and so on and so forth. Okay, what happened here is that the DNS might actually rotate, returning different IP address each time a web browser or an email server looks up for an entry, okay, for the particular host name's IP address. So that way you kind of rotate using different physical machines every time, and therefore distribute the load of the service. Why not centralize DNS? You heard in the previous slides, there are multiple name servers and there's a certain hierarchy behind it. So why not just one? Well, it doesn't take long. At the beginning of the internet, there's indeed just one DNS server. But it doesn't take long that we realize when the machine is off, the entire DNS service is off. And everyone on the internet, unless you can memorize the IP addresses of all these servers, otherwise, there's not much you can do. Okay, it's off. Second, every application that needs to find mapping IP address given the name, traffic needs to go there. So very high volume. It gets really busy at times. And hey, those users that are around this particular server will have short delay, but they will always be part of the world far away from a particular machine. So delay not ideal. Some could suffer forever. And maintenance, this is a tricky issue, but it is indeed a problem. There are two perspectives looking at the maintenance issue. One is that the DNS server software is growingly large. When it grows too large, if you want to make just a tiny little change, you need to what? Turn off the machine, update the code until you can put it back running, right? But all you want to do is just to make a small change. So one small change influences the entire internet. Not good. Second, it's also hard to do the maintenance, right? Because if you want to just do some testing, debugging, you have to take down the entire DNS as well. And when the software grows large, chances higher that you need to do the testing longer, debugging longer. Not good either.
All right, so next video is then to show you how complex the DNS server, the server side of the system is complicated. So let me start from.
Therefore, DNS is not a centralized system, but rather a distributed hierarchical system. And this is how the hierarchy looks like. At the top, the root DNS servers. Second level, the .com, .org, .edu DNS servers. The lowest level, or the authoritative server level, the yahoo.com, amazon.com, pbs.org, poly.edu, ums.edu. So what you're seeing here is, hey, .com further breaks up the namespace, and each of these server at the bottom will serve a small range of the names there are on the internet, right? So distributing the load of the name IP lookup. Now, the process of looking up the IP address in a nutshell is this. Client now wants to get the IP address of, for example, www.amazon.com. What it does is first query the top server and try to find the second level server. Query the second level server, next try to find the authoritative name server, the last level. And then from the last level of DNS servers, finding the IP address for a particular host. And let's talk about each of these name servers a bit more. At the top level, the root name servers. It's connected by the local name server. Now allow me to explain. This local name server is not in the hierarchy. This local name server is actually very, very close to the client. Typically what happens is that a whole bunch of these end hosts sitting in an ISP will be sharing one. So ISP or institutional network will set up a local name server there for all the users in the domain to send the queries. And then this local name server then will relay the queries to all these servers in the hierarchy, right? So in a way, the local name server here is the client of the name to IP lookup service. So a local name server contacts the root server first, right? The root server then will contact the authoritative name server to find the mapping, get the mapping, and then return mapping to the local name server. Now, the trick part is this. Okay, when I say contact authoritative name server, it's not like directly going from the root to the authoritative name server. There's a certain way of rerouting the query until it reaches the authoritative name server. Authoritative name server is really the one containing the name and IP mapping. Okay, the top level knows the second level. Second level knows the authoritative servers. Only the authoritative name servers knows the exact mapping. And you see here, there are not many root servers. There are 13 logical root name servers. But each root name servers now have multiple physical sites. For example, here in Tokyo, there are 5 sites, 37 sites just for the Swedish root server, etc. But essentially, very few of these root name servers. Next, the second and the third level DNS servers. At the second level, we have a bunch of these TLD servers, top level domain servers. They're responsible each for a different top level domains. So top level country domains as well, UK, FR, CA, etc. So essentially, this is the last part of the host name there. And each of these TLD server is maintained by some sort of organization of public interest. Some people call them NGO. So for example, Network Solutions maintain the servers for the .com TLD server and EduCost for the .edu TLD. At the third level, we have these authoritative DNS servers, right? So it maintains the IP host mappings. And it could be maintained by the organization itself or by a service provider if the organization is somewhat small and there are not many entries really. Right? Local DNS server, this I tried to introduce earlier. It does not belong to the hierarchy, 3 levels. It's very special. Each ISP or institution network will set up one, and all the clients in the institution or in the ISP will configure themselves to send all the queries to this local DNS server, which is also called the default name server. So when a host makes a DNS query, query is always sent to the local DNS server. Now, these DNS servers often carry these caches of recent translation. So whenever we get a host to IP address mapping to the local DNS server, of course, forward the answer back to the client. But in the meantime, the local DNS server also keep a copy of that, okay, for some time. And this is for the benefit that if the client is looking for the same name again, okay, same name IP mapping again, then it's conveniently already cached in the local DNS server, avoiding going all the way to the hierarchy. Right? So nice. But be careful. These entries could sometimes go out of date. So while these entries are cached locally on the local DNS server, well, the entry might have been changed in the authoritative DNS servers. Okay, although very rare, but there's a chance. So these local DNS servers, if you think about it, it works more like a proxy server. Okay, it's not exactly client, it's not exactly server. It's something in the middle, helping relaying the queries, relaying the answers. Okay, so helping forward queries into the hierarchy if there's no hit here at the cache.
All right, so I guess the local DNS server, it might remind you of what? In HTTP, we have the proxy server. Proxy server also relay client's HTTP request to the server and relay the response from the server back to the client. And you can cache some of the web objects the clients have requested before on the proxy server. So if you find, hey, similar, you know what? Local DNS is just like the web proxy, the proxy server. Okay, but DNS versus HTTP. HTTP server, there's just always one server. But DNS, you see, there's a hierarchy, 3 levels. The root, there are very few number of these. There are very few of these root servers. But then there'll be the TLD servers, the domain servers. Okay, so there'll be one server for each of the domains. .com, .org, .tw is also one of the major domains, top level domains. And then the last one are the ones really storing the host name IP address mapping, or the nickname to real host name mapping, or the Gmail service to the Gmail server mapping, etc. Okay, so that lowest level DNS server are called the authoritative DNS server. They are authoritative. They are the one who really own these mappings. Okay,
So people who want to correct the mapping, so if you have a server running at home and the IP address has changed, then you need to update to your authoritative DNS server. Okay, this host name that I'm using for my service, the IP address has changed to this new one. Okay, so authoritative DNS servers, of course, will be receiving queries for all sorts of mappings. Authoritative DNS servers might also be getting some updates, okay, from network administrators, okay, when the mappings are changed. Now, this last video is to let you know exactly when someone, for example, Gladi asks, when you are browsing the web, right? So you click on a link, but the link says, hey, go to www.ntu.edu.tw. It's not an IP address. Who's doing the DNS hostname to IP address resolving? The browser there is issuing that command. And that command is actually, it can come in different forms. In Unix-based system, it's called dig, D-I-G. I'm actually not quite sure how it's implemented in the Windows. All right. So once you do dig, or once your web browser calls that command to resolve mapping, here's what's going to happen. And you will see it in the video. Okay. There are actually many steps indirect to finally find the mapping. So far, we've learned that there's a hierarchy in the DNS servers. Here's the top, second, and the third level. And we also know that there's a proxy server there, always working on behalf of the client, sending the DNS queries. So let's try to explain further from the local server here, how the query is forwarded, okay, and eventually receiving a reply. And let's do that through an example. Okay, there's going to be a host trying to reach Gaia.cs, but before messages can go out, CIS poly here needs to find the IP address of Gaia.cs over there. And we're going to illustrate this form of query forwarding. It's called the iterated querying. All right. So what the local DNS server does is to contact the server in the hierarchy. And the server will reply with something like this: name of the server to contact. Okay, someone who might know a little bit better, but I don't have it. So messages looks like this. Root server might say, hey, I don't know about gaia.cs.umass.edu in particular, but you may ask, hey, the top level domain server for .edu. Okay, someone knows slightly better than I do. Okay, but I do know someone who knows better. Right? So that's the general idea. And so the process goes: client here issuing query. Local DNS server now forwards the query first to the root. Root returns the IP address of the .edu TLD server. Therefore, the local DNS server could re-forward the query to .edu TLD DNS. Top DLD DNS does not know the IP just yet, but top level domain DNS does know the IP address of the authoritative DNS server, so that will be sent back. And the local DNS server sends the query the third time, okay, to finally the authoritative DNS server. And finally, the IP address for Gaia.cs comes back to the local DNS server. Local DNS server forward that back to the requesting client and be happy about it. Recursive query is the second form of doing the querying. So local DNS server here will forward only to the root, okay, and not contacting DLD, not contacting the authoritative DNS server. And it will be the root's job to find out what the mapping is. And root doesn't really know the mapping of gaia.cs.umass.edu. So he forwards the query to TLD. TLD forwards to authoritative DNS server, and finally the IP address traversed back. And root DNS server here sends back to the local DNS server. Right? Can you see an issue with this? Yeah, so this way of querying puts burden on name servers that's high up in the hierarchy. There's going to be a lot of query comes to the root, and there's going to be a lot of queries coming from the root to the TLD, although the load on the authoritative DNS server remains the same. Right? So heavy load at the upper level of hierarchies, not good. Keep in mind, there are only some tens of root DNS servers, physical root DNS servers. If everyone is sending the queries always to the root, we could quickly bring down all these root DNS servers. And that's not really a viable solution. Therefore, recursive query is an option that we try to disable at the local DNS server. All right, so that's many ways in direction to try to finally get the mapping. And there are two ways of doing it. Mostly people prefer the iterative one, but some applications might prefer the recursive one. All right, now it's time for quiz 13. This is probably one of the hardest quiz among all. Okay, so here it goes. Hey, some of you might be yelling this. Okay, let's get real. Okay. So I'm actually not quite sure what's the meaning of taking all these courses and exams. You know what? I spend so much time and I'm not sure what I've learned. Okay. Yeah, some of you might be thinking this. Hey, maybe this is enough college education for you. Okay. You want to go out and see the real world and see if you are useful in one way or another. Okay, and so you try to take Mark Zuckerberg as a model, as a role model, for example, and you find that Facebook is lame, Petbook is totally better. Okay, so you think maybe we could create a social net service based on people's passion for their pets and animals. Okay, you make friends because of the pets. Okay, how your pets behave, the breed of your pets, and the illness your pets are suffering from. All right, and we use the pet's picture as the profile picture. Okay, so you think that this is gonna go bigger than Facebook? So probably it's just borrowing Facebook's front page design here. Okay, and by the way, this is Honey, and this is the guy who sometimes meows in Polly's video background. All right, so now, you're starting up a company. You'll be your own CTO in addition to being the CEO, CFO, COO, etc. Okay, now try to structure your Petbook server network so that you can direct all these pet page queries quickly, and balanced among all the servers. Okay. Now, we have already learned 3 applications. Oh, actually, 4 applications in fact. DNS, SMTP, which is email, and we have also FTP. But FTP is very similar to HTTP in terms of the server structure, and it's probably even simpler. Right. So we've seen 3 applications, and each of these applications you see that how they structure their server network, the server side of the whole system. Okay, and so would you implement or model your pet page query server network that's more like the HTTP server network, SMTP server network, or DNS server network? You see gradually, right? So HTTP, simple client server, SMTP, there's like a local mail server or the sending mail server, and then there's another server at the receiving end, right? Gets a little bit complicated, and there are 2 levels of hierarchy for the SMTP to work. And DNS here, you see, wow, root server, top level domain server, authoritative server, and on the client side, there's also a local cache or local server. So think which one you would like to model your server network from. It can be any one of them, or taking the advantage, the strengths of each of these models. And feel free to also add your own idea into the network you're designing. So let me bring up this next slide. This is just to give you a clear picture of the server network of HTTP, a server here. Essentially, very simple. In SMTP, we have a local mail server, which is the sending server that's really close to the client user agent, and then SMTP server. Okay, so you see that the complexity being added seems to be at the client side. But then we see DNS. Ooh, the server side gets complicated. It's not just one server. It's there's a hierarchy and many servers for sure. Okay, so you see that the server end gets expanded. And let me abstract these three architectures this way. So this is this client end gets expanded, and this is the server end gets expanded. And so if we abstract out from the applications they are serving, so you see three types of architecture, right? Very simple one. Oopsie. A very simple one to the one that we expand the client end, to also, hey, we not just expand the client end, but also the server end. All right. So to make it simple for you, maybe you could also just think about borrowing model A or B or C. Or you would like to use C and plus some extra things. Okay. So think about this pet book application that you're designing. And tell me what the server network, okay, including the client side, is going to look like. And you can also think about how you resolve a pet page queries. And it might depend on where you are storing these pet pages. All right. Now, go to the score, and you will see that in channel W5, quiz 13. Yeah, the slides that I just show are all up there. Okay. You know what? And we don't have that much time today. So this is also one of the take-home quizzes, okay, that you'll be experiencing in this semester. You definitely want to gather your teammates and have a discussion. In the process of discussing, of course, you draw and you share how you would like to architect the pet book network. And the other teammates give comments, and gradually you converge to an idea. When you're done, come to W5 quiz 13 to tell everyone what you come up with. It's okay to be elaborated. If the space is a little bit, I think there's a character limit in one post. You can also upload a file, a PDF file, okay? And you can also include like a drawing of your network, the architecture of your network in that file. Okay, good. And with that said, in fact, feel free to start gathering your friends, okay, your teammates, and maybe talking about setting up a time that you guys can talk for longer, discuss for longer. And there's still 4 minutes of time remaining. So what I would suggest is this. We'll start doing the test run early. Okay, good. So with that said, I will call the lecture today ends right here. Okay, and use the time you circle with the teammates and start discussing. Those who would like to do the test run faster than later, here's what I would do. I would play the goodbye soundtrack, and we'll just say goodbye, and we'll close the lecture today. And when the streaming session is ended, feel free to log in and join the Google Meet session here. Okay, good. So bye for today. Okay, bye. By the way, Angel, if I let you in now, you'll be broadcasted out to the whole world. So yeah, let's give the goodbye session for just 1 minute, and we'll come right back and take your Google Meet session join request. Okay, bye. All right, so let me end the session now.